Alright, so now that we know how to add, subtract, and multiply matrices, let's first deal with the next thing. Can we divide them? And the answer is no. There is no matrix division directly. We can kind of simulate, thank you, matrix division by using multiplication of an inverse, but we'll get into that a little later. For now, let's just talk about the fact that there is no matrix division. Okay. Now, because you can add, subtract, multiply, and divide, we have to now just kind of familiarize ourselves with some of the rules of matrix algebra. Just so we don't get ourselves in trouble. We already mentioned some of these, but I'll just mention these kind of a little bit quickly here. The first thing that we have is, and these are the rules that we have with numbers, right? When we're adding, subtracting, multiplying, and dividing numbers, these are the rules that we rely on. Okay, so for instance, with numbers, we have commutativity of addition, right? A plus B equals B times A. We also have that with matrix addition. So if you add A plus B with matrices, that's the same as if you added B plus A. We have the associative law of addition that works, that also applies, that's equals, to matrix addition. Okay, associativity. We have associativity for multiplication. Okay, now that's kind of nice. You can do B times C first and then multiply times A, again provided all the sizes match up, or you can do A times B and multiply by C. And then we have the distributive laws. Oops, let's do it this way. A times B plus C equals AB plus BC, and A plus B, try that again, A plus B times C is equal to AC plus BC. Okay, so those all are on the table. We just mentioned this one, let's do it this way, AB does not always equal BA. So we don't have associativity or commutativity for multiplication. Order matters for multiplication. So just remember that as you're working through these. All right. Now, here's a big jump for us. Thanks to the fact that we have matrix multiplication, we can now tie this to my computer needs to reset or something. We'll see if we can't survive this. Here's what we can do. We can take a system of equations and we can write it like this. We grab the coefficients of the left-hand side. Okay, that's called the coefficient matrix. Notice I'm not augmenting it. And then I can create a column vector of just the unknowns. And now here's the interesting thing. If I multiply those, right, because there's a little multiplication. We call this one A. Let's do it this way. We call this matrix A. We call this matrix X. That should be bolded. and we multiply them. If you take that matrix A times that column vector, you're going to get those three things, right? Because check it out. This row times this column gives you 3x1 plus 2x2 plus x3. Bam, that right there. Okay, so I can write my system of equations as a matrix, the coefficient matrix, times a column matrix of the unknowns, and that will equal, I can set that equal to the right hand side, which we'll most often refer to as B. Okay. So every single system can be rewritten like this. Coefficient matrix times unknown matrix column vector equals solutions vector, or AX equal B. So we have an equation. We have an equation, but notice all of the parts of the equation are matrices. So every system that you have can be rewritten as a matrix equation, and that's a nice matrix equation. In fact, let's give you a preview of coming attractions. If I gave you this equation yesterday and asked you to solve for B, you would simply say, oh, or solve for X. You would say simply X equals B over A, right? But if those are matrices, that you can't do that division, all right? So we'll talk about how to get around that and figure out what X is, right? Because X is the unknown. We want to know what X equals. X equals this, but how do we accomplish that? So when we get into that next section, 3.5, we'll talk about that.